In this we get the product. Here breaking of the carbon-carbon double bond, and we get the two product, that is one is ketone and another is aldehyde. See third example where we have taken here alkene, but these alkene are present in cyclic ring. So ozonolysis process, first step is the ozonoid formation, second breaking of this ozonoid. In the ozonoid breaking, we obtain the product. See here. So we obtain two aldehydes. This compound is called as diol compound. Okay, diol compound. Instead of that, if we use substituted compound, substituted alkene, one substitution is there. Then by the same process of ozonolysis and ozonoid breaking, in the second step we get the product where the breaking of this carbon-carbon double bond. So here CH3 group, double bond O, and here this aldehyde. Okay, and see another example where structure of alkene is di-substituted. We have taken two substitution across carbon-carbon double bond. Two substitution are there. In these two substitution, when first step ozonoid formation, second breaking of this ozonoid. Second step is the breaking of ozonoid. In the breaking of ozonoid, we get the product structure CH3, again double bond O, CH3, C double bond O, CH3, C double bond O, CH3. What is our observation? Observation from these reactions, if carbon-carbon double bonded carbon is a terminal carbon, it is terminal carbon without substituent. If double bonded carbon is a terminal carbon, if double bonded carbon is a terminal carbon, then one of the product must be formaldehyde. If one of the product must be formaldehyde, terminal. See second, if double bonded carbon contain one substituent, then one of the product must be aldehyde, one carbon, one substituent. If double bonded carbon have one substituent, here one substituent is there, due to which we obtain one aldehyde as a product. One aldehyde. One of the product is aldehyde. See, if double bonded carbon contain two substituents, double bonded carbon, if instead of this hydrogen, if CH3 is there, then if two substituents, then resulting product is a ketone. And in case of cyclic alkenes, we obtain the product. In case of cyclic alkenes, I am writing here. In case of cyclic alkenes, which product is obtained here without substituent? We obtain diol, two aldehydes. That is, either product is a diol, or here in case two substituents are there, we obtain two ketones. So this compound is called as diol. This is diol compound. Product is either diol or maybe the combination maybe the combination here, one substituent is there, then we obtain one ketonic compound, one aldehyde compound. So we obtain here C double bond O and one of the aldehyde as a product. So this is the case of cyclic alkene. When our starting alkene is a cyclic, then we have obtained either diol or one aldehyde and one ketone as a product. So one aldehyde and one ketone as a product. So these are some examples of ozonolysis, where if carbon-carbon double bonded carbon is a terminal carbon without substituent, one of the product is formaldehyde. If terminal carbon or double bonded carbon contain one substituent, one of the product is aldehyde. And if it contains two substituent, then one of the product is a ketone. And if cyclic is there, then maybe obtain diol or one aldehyde and one ketone in the product. So that depends on the structure of alkene. So these are some examples of the ozonolysis reaction. And these are some observations from these examples. Now we have to see the applications of the ozonolysis process. Now see the application of ozonolysis process. So ozonolysis application. It is important reaction in organic chemistry. So first application is, this method was previously used. Before we don't know about spectroscopic methods. This ozonolysis process is used for the structure elucidation. So this ozonolysis was used for structure elucidation before spectroscopic method was known. Methods were known. When we don't know about the spectroscopic method for the structural elucidation, then this method, ozonolysis, is used for determination of structure. And see the second application, from number of carbon and arrangement of these carbon in degradation product. We can work back to original alkene. So this is about the application of the ozonolysis process, where structure elucidation for this previously this was used for structure elucidation. Second, from number of carbons and arrangement of carbon atom in degradation product. We know that we obtain degradation product either aldehyde or other ketone, or one aldehyde, one ketone. So these are degradation product from the number of carbons present in the degradation product in aldehyde and ketone, and arrangement of these carbons in the structure. We can work back to the original alkene. We can find out the structure of original alkene from these. So these are about application of the ozonolysis. So ozonolysis application. So these are the reactions of carbon-carbon double bond. Now next topic that we have to study the reactions of carbon-carbon triple bond, because triple bonded carbon also contains pi bonds, pi electrons, which are loosely held, and due to these loosely held electron, the addition reactions are possible for these carbon-carbon triple bond. Carbon-carbon triple bond bonded compound undergoes addition reaction. But the difference is that, like like carbon-carbon double bond, it adds hydrogen, it adds halogen, it adds haloacids, there is addition of water molecule. So addition of these compounds is possible in case of carbon-carbon triple bond also, like carbon-carbon double bond. We also these reactions of carbon-carbon double bond where addition of hydrogen is there, addition of halogen, addition of haloacids, addition of water is there. So all these reactions are possible with the carbon-carbon triple bond, but instead of 1 mole, here required 1 mole because 1 double bond is there and there is addition of 1 mole of these compounds across the carbon-carbon double bond. Here requires 2 moles because 2 double bonds that we have to produce. 2 double bonds that we have to produce. So here in case of carbon-carbon triple bond, 2 moles of these molecules, these compounds required in order to proceed the reaction. Or by using some control condition, some reagents, it is possible to control the reaction at alkene stage only, because from alkyne by addition it is converted into alkene, and by alkene it converted into alkane. Okay, so this is the trend of reaction, but it is possible to stop the reaction at alkene state by some controlled conditions. So by controlled condition we can stop the reaction at alkene state. Another important point, in case of terminal alkyne, so such kind of alkyne, in case of terminal alkyne, one bond excess here. So see here terminal alkynes. In case of terminal alkyne, this hydrogen is there, and this hydrogen, not only due to this hydrogen, the carbon-carbon triple bonded compound, alkyne compound, not only goes into the addition reaction, undergoes addition reaction, but also displacement reaction. Also undergoes displacement reactions. Okay, so displacement reactions are possible due to some acidic character of this hydrogen. Due to carbon-carbon triple bond, this has some acidic character, due to which this hydrogen removal is possible by using some metal reagent, some another reagent, and displacement reaction occurs. So what is overall analysis? Overall analysis says that alkyne undergoes 2 types of reactions, as alkane where only 1 type of reaction. So alkyne undergoes 2 types of reaction. First is addition reaction is possible with alkynes, and also displacement reaction. Due to the displacement reaction is possible with terminal alkynes. Displacement reaction is possible here for terminal alkynes. So displacement reaction gives addition of metal compounds, which is important in organic chemistry. Reactions of metal, as we saw the Grignard reagent, some another metals are added, formation of acetylide compounds that we will see in the reactions. So see, we have to study the reactions, addition reactions of alkynes. Okay, addition reactions of alkynes. So which additions we have to study? We have to study the addition of halogens. We have to study addition of halogens. We have to study addition of haloacids. We have to study the addition of hydrogenation. We have to study the addition of water, and next we have to study the acetylide formation by the metal reagent. Okay, we have to see all these reactions in details. Okay, addition of halogens, addition of haloacids, addition of hydrogen, addition of water, and acetylide formation. So these reactions we have to study in details by mechanism, how many steps are there, which products are obtained, which are major products, which are minor products. So we have to see in case of symmetrical alkenes, in case of unsymmetrical alkenes. So we have to see these total reaction one by one. So before starting this, let's see the general mechanism of this alkyne formation. Addition of alkyne, general mechanism of this addition reaction of alkyne. See the mechanism. Now in the mechanism, just consider here the addition of HX compound, halo acids. HX, it may be HCl, HBr, H2SO4 or some other compound where it's containing H. That means polar compound. So carbon-carbon triple bonded compound, C triple bond C, C triple bond C, carbon-carbon triple bonded compound react with HX. Okay. When it reacts with HX, then first step is a slow step where this carbon-carbon triple bonded compound attacks on this proton, attacks on this hydrogen, and removal of X minus. When this electron density, this pi bond is attached to two carbons first. So this electron density transferred here, and this hydrogen attached to one of the carbon out of these two, leaving other carbon with deficiency of electron. So see, when it is symmetrical, so when this hydrogen attached to this right carbon, then left carbon gets positive charge. When this attached to left carbon, this right carbon gets the positive charge. So one carbon living with deficiency carbocation. Okay, so this carbocation is not called as general carbocation, it is called vinylic cation. This cation is called vinylic cation. Vinylic cation, as this carbon-carbon double bonded compound contains this carbocation, so it is a vinylic cation. Now vinylic cation obtained. So the process of addition reaction in case of carbon-carbon double bond takes place via carbocation, and here process of addition reaction of carbon-carbon triple bond takes place via vinylic cation. So vinylic cation is there in the second step. Second step is a fast step where this nucleophilic compound obtained previously attacks on this, and we get the addition product. So where addition of H and X is there across the carbon-carbon bond. Now this reaction doesn't stop here. Why? Because it also contains unsaturation. So there is tendency of this molecule to react again with another reagent. So another mole of reagent. That's why I said 2 moles required in case of carbon-carbon triple bond. Because here, after first mole of addition, it leaves the compound with unsaturation again, and due to this unsaturation, it again reacts the same way, and we get the addition of another compound here and get total saturated compound. So this second HX addition is there, we will get total saturated compound. So this is general mechanism. In this process, this is the second step. This is first step. First step is the slow step, and rate determining step where both reagent as well as reactant both are involved there. So this is general mechanism of addition reaction of carbon-carbon triple bond, where carbon-carbon triple bond, first is the acceptance of proton by carbon-carbon triple bond, pi bonds of this carbon-carbon triple bond, leaving carbocation, which is called as vinylic cation, and in the second step, negative charge base or negatively charged species attacks on this carbocation, this vinylic cation, to get the product, which again react with another mole to obtain the final product. So this is general mechanism of this one. Now we have to see the reaction of halogenation. addition of halogens.